The art of order, mastering sorting algorithms in modern computing. In the ever-evolving landscape of computer science, sorting algorithms stand as fundamental pillars that underpin countless applications, from database management systems to search engines and beyond. These algorithms are not merely tools, they represent centuries of innovation and refinement aimed at optimizing efficiency, reducing computational overhead, and ensuring data integrity across diverse domains. From ancient Roman numerals to quantum computing architectures, the quest for efficient sorting has driven technological progress through millennia. This article delves deep into the world of sorting algorithms, exploring their historical roots, modern implementations, performance characteristics, and practical implications in real-world software engineering scenarios. The evolutionary journey of sorting techniques. The origins of sorting can be traced back to early human civilizations where rudimentary methods were used to organize physical objects based on size, weight, or other measurable attributes. Ancient scribes employed alphabetical ordering techniques long before the invention of the printing press, laying foundational principles for structured information organization. With the advent of mechanical calculators in the 19th century, sorting became an essential component of automated computation. Charles Babbage's analytical engine incorporated sorting mechanisms designed to handle punched card operations, a precursor to modern digital sorting paradigms. The mid-20th century marked a pivotal era in sorting algorithm development. Early computers faced severe limitations in processing power and memory capacity, which necessitated highly optimized sorting strategies. During this period, several landmark algorithms emerged. Bubble sort, a simple comparison-based method that repeatedly steps through the list, compares adjacent elements, and swaps them if they're in the wrong order. Though its O(n) superscript 2 time complexity makes it unsuitable for large datasets. Insertion sort mimics how people sort playing cards manually by building up a sorted array from unsorted input, offering better average case performance than bubble sort but still suffering from quadratic worst-case behavior. Merge sort, introduced by John von Neumann in 1945, this divide-and-conquer approach recursively splits arrays into halves until reaching trivially small subarrays, then merges them while maintaining order, an O(n) log n solution ideal for external storage environments. These pioneering approaches laid the groundwork for subsequent generations of algorithms that would revolutionize both theoretical research and industrial application landscapes alike. Diverse paradigms in algorithm design. Modern sorting algorithms encompass a wide spectrum of design philosophies, each tailored to address specific constraints and optimization goals. Understanding these paradigms is crucial for selecting appropriate solutions depending on dataset size, hardware capabilities, and desired trade-offs between speed and resource utilization. The primary classification system divides sorting algorithms into two broad categories: comparison-based and non-comparison-based. Comparison-based algorithms rely solely on pairwise comparisons to determine element relationships, whereas non-comparison-based approaches exploit additional properties inherent within the data itself. This distinction carries significant implications for performance analysis and applicability. For instance, the lower bound for any comparison-based sort is (n) log n, meaning no such algorithm can achieve better asymptotic efficiency than this limit. In contrast, non-comparison sorts like counting sort or radix sort can achieve linear time complexities under certain conditions. Comparison-based algorithms, the foundation of traditional sorting. Among the most widely studied classes of sorting algorithms are those rooted in comparative logic. These include well-known examples such as quicksort, heapsort, and various hybrid variants that combine different methodologies for optimal results. Quicksort exemplifies the divide-and-conquer strategy by selecting a pivot element around which partitions form. Elements less than the pivot go left, greater ones right, and recursive calls process each partition separately. Its expected runtime complexity is O(n) log n, though degenerate cases can result in O(n) superscript 2. Heapsort operates by transforming the input array into a binary heap structure, a complete tree satisfying the heap property where every parent node contains a value greater than or equal to its children. Repeated extraction of maximum values yields a fully sorted sequence with guaranteed O(n log n) worst-case performance. A notable advantage of heapsort lies in its predictable execution times compared to quicksort, making it particularly suitable for mission-critical applications requiring consistent performance guarantees regardless of input distribution patterns. Non-comparison approaches, leveraging data characteristics when dealing with integer keys or strings drawn from limited character sets. Alternative sorting strategies become viable options. Non-comparison algorithms capitalize on intrinsic properties of the data rather than relying purely on relative comparisons between elements. Counting sort represents one such technique that excels when working with discrete valued inputs whose range isn't excessively large. It counts occurrences of each distinct element within the input set, constructs frequency tables accordingly, and reconstructs the final ordered output using cumulative sums. Radix sort extends this concept further by considering individual digits, or characters, from least significant to most significant positions. By applying stable sorting procedures iteratively across successive digit positions, Radix achieves full sorting without direct element comparisons. Both methods offer substantial performance benefits over traditional comparison-based alternatives in specialized contexts. However, their effectiveness diminishes significantly when applied to arbitrary data types lacking defined numeric ranges or easily quantifiable features. Evaluating performance metrics and trade-offs selecting the optimal sorting algorithm requires careful consideration of numerous factors influencing overall system performance. Key evaluation criteria include time complexity, space requirements, stability, adaptiveness, and ease of implementation. Time complexity remains arguably the most critical factor determining suitability for large-scale applications. While many algorithms provide theoretically impressive upper bounds, actual running times often depend heavily on constants hidden within big O notation as well as cache locality considerations. Space complexity also plays a vital role in decision-making processes. In-memory sorting versus disk-based operations introduces entirely new dimensions to algorithm selection. One must weigh whether sacrificing some temporal efficiency could yield considerable gains in spatial economy. Stability refers to an algorithm's ability to maintain original relative orderings among elements sharing identical key values. Stability becomes especially important in multi-stage pipeline processing workflows involving sequential transformations of partially sorted structures. Adaptiveness measures how effectively an algorithm leverages existing partial orderings present within the input data. Adaptive algorithms typically outperform naive counterparts when handling already sorted or nearly sorted sequences due to reduced operation counts. Practical applications across industries sorting algorithms permeate virtually every aspect of contemporary technology infrastructure. From operating systems managing file directories to e-commerce platforms organizing product listings, these fundamental routines enable seamless user experiences through intelligent data manipulation. Database management systems employ sophisticated indexing schemes built upon advanced sorting techniques to facilitate rapid query responses. Index creation involves sorting relevant columns to establish hierarchical access paths, enabling logarithmic lookup times instead of exhaustive scans. Search engine ranking algorithms frequently utilize variant forms of sorting to prioritize web pages based on relevance scores derived from complex mathematical models incorporating hundreds of variables related to content quality, link authority, etc. Scientific simulations leverage high-performance sorting implementations to manage massive datasets generated during computational experiments. Efficient sorting ensures timely post-processing phases necessary for extracting meaningful conclusions from raw simulation outputs. Emerging trends and future directions. Ongoing advancements in parallel computing architectures continue reshaping the landscape of sorting algorithm design. Researchers explore novel ways to distribute workloads across multiple processors while minimizing communication overheads that degrade scalability potential. GPGPU, General Purpose Graphics Processing Unit, Acceleration presents exciting opportunities for accelerating sorting tasks utilizing thousands of concurrent threads capable of performing independent computations simultaneously. Quantum computing promises revolutionary breakthroughs in algorithmic complexity theory. Quantum sorting algorithms aim to exploit superposition states and entanglement phenomena to achieve exponential speedups over classical equivalence, an area currently under intense investigation by leading research institutions worldwide. Machine learning integration opens new frontiers by enabling adaptive sorting strategies that learn from past executions to optimize future performance profiles automatically. Reinforcement learning frameworks show promise in dynamically adjusting parameters based on observed execution traces. Implementational considerations and best practices coding sorting algorithms demands attention to subtle yet impactful implementation details that affect correctness, robustness, and performance characteristics. Choosing the right language idioms and leveraging standard library functions judiciously contributes significantly toward achieving clean, maintainable codebases. Language-specific optimizations play a crucial role in maximizing throughput. For example, C++ allows fine-grained control over memory allocations and pointer manipulations, whereas Python prioritizes clarity through higher-level abstractions even at the cost of slightly increased runtime penalties. Understanding recursion depth limits proves essential when implementing algorithms like quicksort or merge sort. Exceeding stack limits may lead to segmentation faults or excessive memory consumption, undermining reliability expectations. Profiling tools help identify bottlenecks by providing granular insights into CPU usage distributions across different parts of the program flow. Visualizing call stacks enables developers to pinpoint areas needing optimization efforts efficiently. Educational resources and further exploration for aspiring programmers seeking deeper understanding. Numerous educational resources exist spanning academic textbooks to interactive coding platforms featuring live visualization tools demonstrating step-by-step execution processes. Prominent publications such as Introduction to Algorithms by Corman et al., commonly referred to as CLRS after its author's initials, serve as authoritative references covering core theoretical foundations alongside practical implementation guidance. Online communities dedicated to competitive programming regularly host contests challenging participants to implement efficient sorting solutions under strict time constraints, fostering continuous improvement skills through peer review feedback loops. Specialized libraries containing optimized versions of classic algorithms accompany many programming languages, allowing users to benefit from decades of accumulated expertise encoded within battle-tested implementations. Conclusion: sorting algorithms remain indispensable components of our digital ecosystem, continuously evolving to meet changing technological demands. Their influence spans from basic arithmetic operations executed billions of times daily to cutting-edge scientific discoveries pushing boundaries of what we thought possible only recently. By mastering these foundational techniques and staying informed about emerging innovations, developers empower themselves to create more efficient, scalable, and innovative software solutions applicable across diverse industries ranging from finance to healthcare to entertainment media production pipelines.